Where am I? Yeah, by the way, the boards that have a texture to them are much better in VR. Writing on that kind of plain plastic feels very kind of cheap.
Is it easier to like see where?
Oh yeah, it's not just aesthetic. It's much, yeah, it's much. It's sort of much easier to control the pen when there's a texture to judge the distance or the plane of the board.
Cool.
Okay, so here I mean differentiation in the sense of calculus, right? Versus Euclidean division in the sense of polynomial division. So and by the end of this, I think you'll hopefully agree that they're obviously related and very closely related. And this is actually the beginning of a rather deep thread in algebraic geometry. So I hope to evoke here something that kind of connects to many interesting topics you might see later if you continue with this journey. So the first remark to make is that polynomials are easy to differentiate, right? I'll just say diff. And well, that's because we have this formula. We can just do it synthetically, so to speak. So a derivative is defined by a limit, but in the case of a polynomial, we have the first thing you learn in calculus class, which is this. For n greater than or equal to 0. In the case where n is 1, where n is 0, you just count this as giving you 0 on the right-hand side, rather than thinking about 1 over x. Okay, so what that means is that we can define d dx as a linear operator on the polynomial ring. I'll just talk about one variable polynomials today. So there's this linear operator. Without doing any limits at all, right? Because I just look at this thing and I say, well, there's a vector space that has a basis consisting of all the powers of x, right? So every polynomial is a linear combination of powers of x in a unique way. And then I can use this formula to differentiate each of those powers of x and stick the coefficients back in front of them. And that way I define a linear operator on the polynomial ring, which is differentiation, but I don't have to take any limits. I just take this formula as an input and then define it. You could see that's kind of cheating because, well, how do I know this as my input? All right, so maybe that's part of what I'm going to answer. We'll see. Let me check my notes. Okay, so let's prove something about differentiation in the polynomial ring that we usually prove by calculus, just to get the flavor of how this works. Okay, lemma. If fx is a polynomial, then this is the Taylor series expansion. So I differentiate f n times, and I set x equal to 0 in the resulting, right? So this polynomial here, I set x equal to 0, and then I stick an x to the n here. Well, let's prove this. I mean, this is a finite sum. Maybe that's the first thing to observe. Why is this sum finite? You in the front row. I can point at people with my pen now. Why is it a finite sum? Radius of convergence. Oh, but we're all on all. That's true. Yeah, how can I point at people and intimidate them if they can't even see me? That's I'm pointing at you, Matt. I just have to name you. Point at the
Okay.
orcam. That's up there.
It's
Yeah,
because
you.
the polynomial has a finite degree, and you
Yeah,
can only
that's right.
differentiate finitely many times before you get 0.
That's right. So if you take n very large, I mean, f has a fixed degree. If you take n very large, then by the formula, you take enough derivatives, you're going to lower the power until you get 0. So that sum is finite. Okay, so it's a polynomial, right? I mean, I said evaluated x equals 0. So this thing here is, in fact, in k. It's a scalar. So that's a polynomial on the right-hand side. It's a polynomial on the left-hand side. They could be equal. Well, how do we prove it? Okay, it's actually easy because the left and right-hand sides are both linear in f. Yeah, this z-index issue is cropping up now. Okay, the left-hand side, what I mean by that is if I replace the left-hand side by f plus g, Billy's trying to get into the board so he can see the parts. Yeah, so what I'm referring to is, if you come over here, Billy, have another look. So if I hold the pen, can you see it go, see the gap between the strokes and the board? Wow, don't do that. Thank you.
I gotta get the camera just right to see it, but I can sort of, I can eventually
Yes.
see it.
So there's a significant gap between the parts and the board, and my pen fits in there. But the VR triggers when I actually touch the pen to the board, so the strokes aren't appearing where I appear to write. So this is one thing we have to fix. It's kind of cute to have you standing over there. Okay, so they're both linear in f, right? The left-hand side. What I mean by that is if I replace f by f plus g on the left-hand side, well, if I replace f by f plus g in here, so I take all these derivatives of f plus g instead.
The m's. Is that not immediate? Which is why we
Yeah,
can't
that's
use
it.
that.
Yeah, that's right. That would be okay. That's sort of halfway between this and what Patrick was suggesting. So let me discuss that first. Yeah, why do we know that we can write f as a polynomial in x minus a? In fact, that is possible, right? It is possible to write f as a sum, let's call it I, of coefficients. These are scalars, x minus a to the I. Does someone want to give a quick argument for why that's possible?
Is it just back to the division again by x minus 8?
Yeah, that's right. That's one way of thinking about it. Yeah. So you take f, start dividing by x minus a, get your quotient and remainder. The remainder has to have degree less than x minus a, right? Which means it has to be a constant. So you divide by x minus a, then you've got a quotient, divide that by x minus a, get a remainder and a quotient, divide the quotient by x minus a, keep going, and you'll produce these coefficients here. And this is essentially the strategy for proving this that I think Patrick had in mind. So that's what we'll do in a moment. There's another way of thinking about that. So maybe let's get over this board over here. Sorry to teleport through you. So maybe there's two comments. So let me make one point about sort of polynomials in x versus polynomials in x minus a, and how you could show that you can write anything as a polynomial in x minus a if you wish, and then we'll come back to the extended lemma and Patrick's suggestion there. Okay, but to come back over here, okay, here's something I can do. I can take f. Well, let me not write the letters. Let me define phi of f to be f with x minus a substituted. X plus a substituted. Right? Everywhere you see x, stick an x plus a. And let me define psi of g, f and g are polynomials, to be g with x minus a substituted. Well, you'll agree that psi after phi is the identity map on polynomials, right? Because psi of phi of f, it looks inside f everywhere it sees an x. First, it substitutes an x plus a, and then it looks inside that thing, and everywhere it sees an x, it substitutes x minus a. But I happen to know that that's the same as substituting just x. Oops, that's not a... it's the same as that. Did I write this in a funny way? Yeah, okay. I'm going to have to... My tethering cord to the real world is pulling me backwards. Okay. This is psi of f of x plus a. Does that make sense? Which is f. Okay, what's that got to do with anything? Why does that actually prove the thing that I was asking about? Why does this, what's on this board, prove that everything can be written as a polynomial in x minus a?
So you've got a bijection essentially between the two rings, or the two polynomial rings.
Mm-hmm. How do I get this expression? Yeah. Sorry to give you a whiplash with the orb cam. I need some way of pointing to things that's a bit more. That's the one good thing about being in VR, right? I can point to things. This formula here. How do I get such an? How do I prove such an expression exists with scalars AI from this discussion here?
I feel like you're going to take the inverse of one of the maps. I guess the inverse to each other.
That's right.
It seems intuitive what you're going to do, but I'm not exactly sure how to.
Yeah, I think that's right. It's kind of just a matter of knowing the right way to write it down, I think. Okay, so take f. So we know, so what is it? Phi, right? So phi f is some polynomial, right? So let's write it out. It is some polynomial. Let's write it out. So, I mean, the coefficients there are obtained by substituting x plus a in for x and expanding out all the brackets, right? And then I've got some AIs at the end. And that's that expression on the right-hand side here. But that means that f is equal to psi of phi of f. And psi of that sum, whoa. Well, that's just going to reach inside there and replace all the x's by x minus a's. Okay. Now, Patrick's suggestion is more algorithmic, right? Because what he's saying is an algorithm for determining, I mean, I kind of gave you an algorithm. I said substitute x plus a in there and expand out all the brackets. okay, that's an algorithm, but I could also do division, which seems like it's different, but in fact it's the same thing. Okay, so let's try this other strategy over here. So the second strategy for proving, we still haven't proven that equality, by the way. I guess, well, okay, there's another proof now available, right? So let's maybe, Patrick's suggestion keeps getting delayed. It's not because I don't like it, Patrick. It's my favorite one. But okay, to come back to this here, what's another proof of this that we can give using what I just said? Actually, maybe I'll leave that question with you. So have a think about that. I'll leave that as the kind of follow-up point, and I'll get onto the division as a way of proving it, because this is kind of actually the point I want to make. I think we'll jump over to the next set of boards. So follow me, please. Okay, so we're going to suppose we're given a polynomial, and I'm going to start dividing x minus a into it. Okay, so divide by x minus a, and then I get f equals some q times x minus a. Yeah, I was just a minute ago writing these brackets to mean evaluate something at x minus a or make a substitution. So I hope this is clear. It's a bit awkward to spell it out any more than that. Yeah, okay. Dot. Why is my camera moving up and down in some strange way? Just a second. I think it's because I'm not on solid ground here. Plus a remainder. What's the remainder? I don't have to write R. I can write something much
F
more
of
useful.
A.
Yeah, very good. Okay, where, yeah, that's fine. I guess we've just been discussing this in MAG, so that's why I asked the question. But if you haven't been thinking about this recently, if I just had an R here, remember the R for the division algorithm has to have degree less than the thing I'm dividing in, which is x minus a, which has degree 1. So this has to be an element of the field. How could I prove from this expression that it's indeed f of a?
You evaluate both sides at a. At x equals a.
Yep. So substitute x minus a, x equals a rather, gives, well, the left-hand side gives me f of a. The right-hand side, this term vanishes, so I'm just left with r. Okay, and this idea of extracting the meaning of the output of the division algorithm by making substitutions is the core of the connection between differentiation and division. All right, well, this is fine. We could stop here, and this is kind of where we got to in the course, but why not continue, right? Nobody stops me from saying, well, now let's do it again, but on Q. So that's what I'm going to do. Maybe I'm going to call this Q1 because I'm going to keep doing it. Okay, so divide again. Okay, so we can say Q1 is equal to Q2. Well, maybe not. Maybe I stopped on the first board. Under what circumstances would I have stopped? There's a case under which
had, if Q1 had degree 0 or was 0, I guess.
That's right, yeah. So if, I'm on my tippy toes now, if Q1 has degree greater than or equal to 1, if it's already degree less than, I mean, we could still do the division, it just wouldn't give us anything here. We just get the remainder straight away, right? Okay. I suppose I could write R as Q1A, right? I don't know if I really need to do that or not. Maybe I will. Okay, so this is Q1A. Okay. So what is the meaning of Q1A and Q2A? What are these numbers? How would I mean, maybe you can think back to the earlier board and know the answer. That's good, but even better would be an answer that makes sense purely in the context of these two boards. How can I figure out what Q1A means, for example? Let's go back to that formula that defines. Okay, so the formula for Q1 says F1, or F rather, is equal to Q1, that's a polynomial in X, times X minus A plus FA. Okay, well, let me subtract. Let me just get reoriented here. Let me subtract the FA over to the left-hand side. So that's FX minus FA. And then I've got X minus A on the right-hand side. So let me divide that through. Now, strictly speaking, this is just by definition Q1, and it only really makes sense because I'm in a domain and so on. But okay, but this format looks familiar to you, so I'll write it. That is equal to Q1X. Okay, so what's Q1A mean? Well, it's what I get by sticking X equals A in the left-hand side, which doesn't seem like it is defined, but it is, because that ratio is a polynomial in which I can substitute X equals A. So this is Q1A. What's the left-hand side? That's by definition, at least in the calculus sense, F prime A. I'm cheating a little bit here, you might notice, right? I'm kind of inviting you to switch back to your pre-existing notion of derivative so that you look at the left-hand side and say, well, that is also the limit as x goes to a of fx minus fa over x minus a, which is the derivative. So I suppose I'm begging the question a little bit, but I'm going to roll with it anyway. Okay, so hopefully you see now why the quotient and its value at a is the derivative, why that makes sense. Okay, so what about Q2 of A? Well, it has the same relationship to Q1, so Q2 of A has the same relationship to Q1 as Q1 of A does to F, right? Almost. Okay, let's just proceed. So any questions about this? This makes sense. So the first quotient, when you evaluate it, computes F prime. I guess we can continue to do the second derivative. Maybe it's already pretty clear. Maybe I'll just expand out this first step and leave it at 2 steps. So f is equal, if I write q1 as q2 x minus a plus the remainder, which I argued was q1a. That was all times x minus a, right? Plus the remainder of the first step, which was fa. And then if I expand this out, I get, this is q2 x minus, oh, I guess I'll change the order because that fits with the formula from earlier better. That's fa plus q1a x minus a, which is f prime a. X minus a. And then I've got this term q2 times 2 copies of x minus a. So that's plus q2. Now this is a polynomial, right? I'm not going to write q2a there. That wouldn't be correct. Okay, so inside here, I can keep dividing. And hopefully you see the pattern, right? The coefficient of x minus a will give me the next order thing. The remainder here will be q2a, which is f double prime a times 2, and so on. Right? Okay. Maybe you're wondering where the 2 comes from. I think that's a good exercise for you to understand, so I won't spoil it for you. Okay, so we can just keep dividing x minus a in, and the remainders we get at each stage are the derivatives of f at a. This is the meaning of iterated Euclidean division and its remainders. It gives you exactly the derivatives. So that's the connection between iterated Euclidean division and differentiation. I had more to say, but I'm not sure of the time. Can somebody tell me how much time we have left?
It's 12:35.
All right.
12:35. Yeah, I guess we should stop then. Yeah, okay, I'll stop there and open it the floor to questions. I guess we have metauni dev after this, so we can go a few minutes over if there are questions. So the thing I was planning to say, I guess I'll post the notes on the Discord, is that you can do all of this parametrically in A. So rather than have A be a number, you can have it be another variable. And instead of dividing by x minus a, divide by x minus y. And that's kind of amusing. And by the way, this is how algebraic geometers do calculus. We don't have limits. We only have polynomials, but it's okay. We can do everything we need to do. Okay.
Cool, thanks. This was fun.
Yeah. Okay, we'll leave it at that. Feel free to wander around and explore this pocket. I'm going to be getting out of the headset and getting into Discord for metauni dev. Okay. Keep it cool. See you later.
Cool. Thanks. Yep.
Thanks, Dan.
Now, okay, this is the best bit. Okay, watch as I collapse into a disgusting ball of bits as I take off my headset. Are you ready?
Oh, yeah.
Oh no.
Looks like a horror movie. Can we kick him?
You've been invited.
See you guys later.